Hello everyone, I'm Norman Wahlberger and welcome to Algebraic Calculus. In this relatively short video, we are going to bring together some maths and some physics. We're going to talk about affine combinations and barycentric coordinates and connect it to centers of mass. So the situation is something like this. We have a triangle in the affine plane, A, B, C, and we have an additional point K. Now we want to think about expressing that point K in terms of the three coordinate points A, B, and C. So we want to think of A, B, and C as temporarily a reference frame and then express K in terms of those. And we're going to see that we're going to be able to do that in a very nice and natural way, just using the algebra of points and vectors and the way we've, in a somewhat novel way, allowed ourselves to combine them. All right, so we're going to see that, like to this point K, we're going to be able to give the expression 2a plus 3b plus 6c over 11, or 2/11ths of a plus 3/11ths of b plus 6/11ths of c. And that's an affine combination because it has the unique property that the sum of the coefficients equals 1. Okay, sum of coefficients equals 1. So this is a combination of points in the plane, and generally we're not allowed to combine points, but affine combinations we are allowed to. We have some meaning associated to that. And connecting to the physics, what ends up happening is that these numbers here, these coefficients, can be interpreted as being masses that we could put on a triangle at the three vertices in such a way that this point K would be the center of mass. So if you think of this triangle as being horizontal, has these three masses and otherwise is weightless, the place where the triangle is going to balance, assuming we have 2 units at A, 3 units at B, and 6 units at C, would exactly be this K here. So we're going to talk about that. And so this is a triple of numbers, 2/11ths, 3/11ths, 6/11ths. We can call that barycentric coordinates for the point K. This was essentially introduced by Mobius near the beginning of the 19th century. And we're going to see that this way of expressing K is very flexible. First of all, it doesn't require K to be in the interior. In this case, it's in the interior. But if we allow negative weights, which we already have some experience for, then we can get K pretty well anywhere in the plane, in fact. Okay, so it's a very flexible kind of and useful kind of notation. And we'll also see that it connects very naturally with vector proportions, that these numbers here are intimately connected with these ratios here. So for example, along this side here, you see that this point here, where that Cevian meets AC, divides that up into the ratio 3:1. So we're talking about vectors, that vector compared to that vector is in the ratio 3:1. And that's exactly what we need so that this thing here would balance if we had masses of 2 and 6 here by Archimedes, a law of the lever. So the barycentric coordinates allow us to read off all kinds of interesting information about the relative positions of these various points along segments. It's a surprisingly powerful and really beautiful application of really very elementary vector ideas. It's basically all about affine geometry. So to explain those things, let's go to the one-dimensional version where we just have 2 points forming a segment in the plane. So points A, B, and C is some additional point on that line. We'll draw it in the interior there. Now in this case here, this point C can be written as the point A plus 1/3 the vector AB. So here's the vector AB from A to B. If we take roughly 1/3 of it, then we get a smaller vector, which, if we wanted to draw it, it would be like this. Okay. So that would be 1/3 of this vector V. And if we take the point A and we add this vector, then we get the point C. So that was one kind of novel notation that we introduced. And then a second novel notation was to think about the vector AB itself as being a difference of points. We can replace that with just B minus A. When we do that, we get A plus 1/3 of B minus A, and it's natural to just reorganize that so that we have 2/3 of A, because there's a plus A and a minus 1/3 A, so that's a total of 2/3 A, plus 1/3 of B. So we see that by combining these two notational devices, we naturally express the point C as an affine combination of A and B. The coefficients sum to 1. And this expresses the fact that the point C is closer to A because the weighting of A is bigger than the weighting of B. So we now have barycentric coordinates. We can say that the point C has barycentric coordinates 2/3, 1/3 with respect to A and B. So it's a way of describing points on the line A, B as weighted combinations of A and B. And the actual weights involved, well, it actually connects directly with Archimedes' law of the lever, because if we think about this segment sort of placed horizontally, subject to gravity, then C is exactly the place where it will balance if we put a mass of 2 here and a smaller mass of 1 here. Okay, it'll be 1/3 the way along. So that gives us another interpretation of what these masses are. Whether it's 2 here or 1 here, or we could replace this 2 with a 2/3 and this 1 with a 1/3, okay? That's just a renormalization. It's not going to affect the balance condition. Then we see that these barycentric coordinates are just the masses that we could put on A and B so that everything balances at C. Okay? So it's a nice combination of maths, affine geometry involving vectors, and the physics of basically balancing Archimedes' law. And so here's the general version of that specific example. Points A and B, C somewhere on the line. V is the vector AB. So if we think of C as being the point A plus some multiple lambda of the vector AB, then if we replace the vector AB with the combination B minus A, then we get, by a little bit of rearrangement, 1 minus lambda A plus lambda B, expressing C as an affine combination of A and B, because the total is still 1. And we get then this correspondence, and we can say that the numbers 1 minus lambda and lambda, this pair, they are barycentric coordinates of the point C with respect to A and B. And just to check the balance condition, this is really the same as saying that if we put masses 1 minus lambda at A and lambda at B, then the point C will be the place of balance. And we can check that that's true by just looking at some vectors. We've said that that's the vector lambda AB. Since that whole vector is AB, this little remaining vector here from C to B must be 1 minus lambda times AB. The difference between AB and lambda AB is 1 minus lambda times AB. And then if we orient things so we're talking about vectors emanating from C, then we should change this one to this vector in this direction, which would be minus lambda AB. And then we can check the balance condition, because the mass here times the vector, there's the mass, there's the vector, plus the mass here times this vector, there's that vector there, is identically 0, because here we have 1 minus lambda times minus lambda, and here we have plus lambda times 1 minus lambda, and they all cancel, and we get balance according to Archimedes. So the physics is giving us a mental image, a mental physical intuition about what it means for the point C to have coordinates 1 minus lambda lambda with respect to A and B. But that actually was just derived purely vectorially using just this framework of affine geometry. And so now let's have a look at the two-dimensional version of that, where we're not just going in one direction, we're going in 2 dimensions. Okay, so the picture might be like this. We have some coordinate framework, our affine plane set up some way or other. And here we have 3 points, A, B, and C. And we're interested in expressing things in terms of these 3 points, A, B, and C. For example, here's a point K, somewhere in the plane. How could we describe that with respect to these points here? Well, a natural thing is to consider the component of this K in this direction and in this direction. Okay, so we try to find lambda AB. AB is the vector from here to here. Some multiple of it, which is that vector there. And some multiple of the vector AC, say mu AC. from here to here, such that when we start here and we add these two respective displacements, we end up with k. Algebraically, k is a plus lambda ab plus mu ac. This plus this vector gives us k. Okay, and then we can do the two-dimensional version of what we did in the one-dimensional case. Replace the vector AB with the difference B minus A. And replace the vector AC with the difference C minus A. And then we group things together. There's some A's here. There's a minus lambda A. There's a minus mu A. So altogether, 1 minus lambda minus mu A. Plus a lambda B plus a mu C. And we see we have an affine combination. We're expressing k as a combination of A, B, and C with the crucial property that this number plus this number plus this number obviously equals 1. That's an affine combination. And these three numbers then, 1 minus lambda minus mu, lambda, and mu, can be called barycentric coordinates of the point K with respect to A, B, and C. The first is the coordinate of A, or the coefficient of A, the weighting of A. The second is the coefficient or weighting of B. The third is the coefficient or weighting of C. And the coefficients sum to 1. Okay, so to illustrate this, let's return to the example that we started off with. We have 3 points A, B, and C, and this point K, which is written this way. 2/11ths of A plus 3/11ths of B plus 6/11ths of C. Now, this is a very useful and flexible kind of expression because we can manipulate it, as it turns out, in lots of different ways. So let me show you one very nice way of doing this. So let's say we take the 2/11ths of A and we sort of choose to combine these two. Okay, combine them, just algebraically. So I want to have an affine combination at the end, so I'm going to just have one object here. So if there's 2/11ths of A, I'm going to want to have 9/11ths of whatever this is, because I want an affine combination summing to 1, right? Okay, so I'm just going to put a 9/11ths here, and I'm going to ask myself, what do I have to put here in order that everything balances? Well, in order for the combination of B here, the coefficient to be 3/11ths, I better put 3/9 as the coefficient inside there. And in order for the total coefficient of C to be 6/11, I should put 6/9. Then everything will work out, and this will actually be equal to that algebraically. And what we've done is now express the point K as a combination of A and this new point. Let's call it D. 2/11ths of A plus 9/11ths of D. What does that mean? Well, what is the point D? D is this thing here, which if we simplify it, is 1/3 of B plus 2/3 of C. So where are these various points? Well, D is 1/3 of B plus 2/3 of C. That's a one-dimensional kind of weighting that we have already seen. That means that this D over here is in the proportion of 2 to 1. It's closer to C because the weighting of C is bigger. That's 2/3. And this formula is telling us that the point K that we're starting with can also be expressed as a combination of A and this point D. In fact, with weightings 2/11ths and 9/11ths. That's telling us another proportion. There are actually quite a lot of proportions here that we can sort of read off from this. So this is in the proportion 1 to 2. We've just established that. And this is telling us that we're actually in the proportion of 2 to 9. Right, so this segment to this segment is in the proportion 9 to 2. More precisely, this vector to this vector, that vector proportion is 9 to 2. Okay, so there's lots of other things that we can do with this. For example, if we compare this expression to what we just did on the previous thing, we can see that we can also write it as a combination of the vector AC and the vector AB added to A. So what is this vector U going to be? Well, let's start with V. V is going to be, well, it's some combination of AB that we have to add to A. That's exactly the coefficient of b there, the number that was lambda in the previous slide. So v is equal to 3/11 of the vector AB. That's telling us that if we go in this direction 3/11 of the total vector, then we'll be in the right position to go over to k. And in this direction, the mu, the u vector will be some combination of AC, and that combination is exactly 6/11. 6/11 of AC. And so this k can also be written as that 3/11 of this vector plus 6/11 of this vector added on to A. And an interesting similar kind of analysis can be done from the points C and B. Everything can be read off ultimately from this one barycentric expression. These numbers 2/11, 3/11, and 6/11. And the beauty of it is that this all corresponds to Archimedes balancing, because exactly the same numbers appear in terms of the masses that we have to put at these 3 points in order for K to be the point of balance. Masses are 2, 3, and 6. Or if we renormalize to make it look exactly like what we have up here, 2/11, 3/11, and 6/11. That way they would all add up to 1. So there's some nice things that can be read off. Let me just do the rest of it. So we've said this is in the proportion 1 to 2. What's the proportion here to here? Well, this is weight 3, this is 2. This is going to be in the proportion 2 to 3 for balance. 2 to 3. And here we have 2 and 6, or same as 1 to 3. And that means that this is going to be in the ratio of 1 to 3. So another way of thinking about this barycentric combination is it's telling us sort of all at once what the various proportions here are that the Cevians make. 1 to 2, 2 to 3, and 3 to 1. And so from a mathematical point of view, the fact that this all works really is boiling down to Ceva's theorem, which tells us that the product of 2, 3, and 1 should be the same as the product of 1, 2, and 3. Or if you think in terms of proportions, 2 to 1, 2/1, times 3/2, times 1/3 should be 1. So there's a kind of a lovely concurrence of vector geometry and balancing of physics. And that's very nice because we want to be motivated by the physics. We want to have a theory which applies to physics and tells us something about the real world. But we also want to have a mathematics which is independent of the physics. The logical structure is independent. And I'm hoping that you can kind of see that there's a logical structure just having to do with points and vectors, okay? And that just using the algebra of these points and vectors, we can basically get at the physical questions. We can answer the questions that the physicists might be interested in. And in fact, calculus has a lot of applications to centers of mass. That's a very important kind of application of integration ideas, which we'll see more of as we carry on. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.